If you heard that a big moon stabilizer is necessary or even a solution to the Fermi paradox, I think it's time we looked at the actual literature. Welcome to Seti Astro. So for the last few videos we've been building up here. We've got gravitational influences and magnitudes between the Sun, Earth, and Moon, accurate lunar and Earth orbits around the Sun, the gravitational potential wells of all the planets in the solar system. Then we got into actual torquing forces on the Earth itself, the gravitational field around the Earth, including a quadrupole moment, calculating the precession of the Earth based on the major contributors of the Moon and the Sun, even charting those effects across the next 60 years, which is caused by this nodal cycle, which also causes a nutation of the planet's wobble too. So all this is leading up to the point that now we could discuss what a big moon stabilizer is, the only handful of studies really around it, talk about the other planets, and try to break down the idea that the Earth needs a big moon stabilizer for kind of life as we know it, or a Fermi paradox situation. And it's really hyped up out there. So now you know what is torquing on the Earth and causing the precession. Well, what can happen is if the precession gets slow enough, the tilt of the Earth itself can start exchanging angular momentum with other objects in the solar system when they meet a certain resonance. So just like you can see the example of somebody holding a bicycle tire that's spinning, and then you tilt it and then you start moving, it's exchanging angular momentum from the bicycle tire to you in the spinning chair. The same thing can happen to the Earth itself by exchanging angular momentum with other solar system objects. If the precession gets slow enough, it can meet a resonance with those objects. So that is the basis of the big moon stabilizer, but we're going to get into all that by a lot here. So here I have a plot, orbital distance of the moon from the Earth and the precession speed. So we're going to have to zoom in here a little bit. So today we're at, just over 50 arc seconds per year. Now these other bands down here are the times where it could start resonating with other objects in the solar system. The biggest one that it could start resonating with is Saturn, if our precession rate dropped to 26 arc seconds per year. And we can kind of go in further here. So if there's no moon, the dotted line down here is just the effect from the sun. And you can see it's below where it would be possible to exchange angular momentum with Saturn. The other node here for Earth is just one of the major frequency nodes of the planet itself. Mars is in here as well, but Mars is much smaller than the Earth, so there's not going to be a big exchange of angular momentum there. But that's really where the concern lies. If we didn't have a moon and we were relying solely on the sun to drive our precession speed. Now, bodies like Venus and Mercury are closer to the sun, and remember this tidal force, this torquing force, is with the radius cubed. They're closer to the sun. Their precession rates are completely dominated by the sun. No other solar system body is going to be able to resonate with them due to that. It's just Earth is kind of at this line of demarcation where if our precession rates does get slow, it has the possibility of resonating with some of these other solar system bodies that could exchange angular momentum and actually tilt the Earth. Now let's go into the studies and see where this idea of a big moon stabilizer comes from. And I don't know how else to say it, but why all the other science communicators out there are just wrong saying it's necessary to have a big moon stabilizer. Because recent ensemble models just don't show it, and they're pretty much repeating stuff from 1993, which has been updated since then. So let's get into it. Now you may be surprised to learn, but there's really only a handful of studies done on this at all. And when I mean a handful, I mean like a handful. There's like 3 studies and an abstract. So when you hear big moon stabilizer, really where that is coming from is this 1993 letter to nature that we're going to get into. But here's the timeline. 1993, there's a letter to nature by Laskar et al., which is the one where you are going to hear that the Earth could swing wildly between 0 and 85 degrees in the span of a few millennia or million years, wildly changing the climate. That is just not how you're supposed to read that paper at all, even though it says it in the conclusion. Moving forward in the timeline, 2011 and 2012, Laskar et al. Does a huge ensemble model, huge amount of variables, big time calculation over 4 billion years, thousands and thousands and thousands of initial starting conditions. Their outcome is completely at odds with the 1993 outcome. And then in 2013, there's an abstract that comes out and says that our moon's just on the edge of it being too big, where it's going to cause instability. So if we were in a solar system where maybe Mars had a really big moon associated with it that was causing instability, we may have been saying life here on Earth needed a smaller moon that didn't mess with its stability. So it's just interesting to think of that too, that we may have some bias here since we're here and we have a big moon. And then in 2014 is an analytical study pretty much corroborating the 2012 study. So let's get into these papers. So the main point where most people get the big moon stabilizer bit is really from this 1993 paper. It's a letter to nature, and it says right here that if the moon weren't present, torque on the Earth would be smaller. Chaotic zone would extend from nearly 0 degrees up to about 85 degrees. This is the one that says, the Earth could wobble from 0 to essentially on its side, causing massive climate shifts and all that. So this is just a short. It's a quick letter to nature over the simulation where they're starting at the start of the solar system. So it's a very fast spinning Earth. It's using the current secular orbits of everything. It doesn't take into account anything about gas giant orbits changing and a whole lot of things. Really what it boils down to is it says that with the moon, the precession rate stays above a certain level and stays well away from a chaotic zone. In the Earth, and the precession rate needs to drop to about 25-ish arc seconds per year, and we're up, in 56 arc seconds per year. And the big moon's going to help maintain that. But all in all, this scary claim about, without the moon, the Earth would just wobble from 0 to 85 is based on this article. And it's just, again, it's a short, and it's really there to confirm that a big moon early on would have helped stabilize it and keep it away from these resonances if the whole solar system was the same as it is now as it was then, which we know it isn't. So it's really just a quick article demonstrating on the importance of the moon helping stay out of these resonant periods where the tilt can change dramatically. And I think a lot of people just overread into this, that the Earth could go from 0 to 85 degrees in the span of a few million years. And I know that's what they say in here too, but that is not how you're supposed to read this article. And we're going to see in later work that did full ensemble simulations now. So again, this is it's a small study, only across an 18 million year period, starting with initial conditions from 0 to 170 on the tilt in 0.1 degree increments. So it was fairly detailed in that regard. But this is where everybody gets that idea, 0 to 85 degrees in a few million years. And later work just shows that's not the case. But this article is the one everybody keeps hedging on, that claim about a big moon stabilizer is necessary for the stability of the climate and to lead to technologically advanced species and things of that nature. The next big study on this was it was done in 2011. It's called Obliquity Variations of the Moonless Earth. And this one is a much more detailed numerical analysis of the tilt of the Earth, the orbits, just a whole bunch of things using many ghost planets, they called them, to simulate the whole solar system, varying the initial conditions of each kind of ghost planet just by a little bit, and developing huge ensemble models to look at this. And it's a direct result of these individuals trying to correct the overemphasis on the 1993 letter to nature about the obliquity varying between 0 and 85. And it says right here in the abstract, this has left an impression in the astrobiological community that a big moon is necessary to maintain a habitable climate in an Earth-like planet. But in their case here, with their large ensemble model, and they did it over a 4 billion year period instead of just an 18 million year period, well, they do find the tilt of the Earth changes to a greater extent than our current moonless Earth over hundreds of thousands of years. The obliquity remains within a constrained region, typically between 20 and 25 degrees, over hundreds of millions of years. Now, that's not what you're going to hear from any channel talking about this, where they say a big moon stabilizer is necessary. And again, it goes back to that 1993 letter to nature. And, this is a direct ensemble model that is much more detailed than the 1993 one, going into a 4 billion year period with a whole bunch of, ghost planets, starting conditions, initial obliquity ranges, and just much more methodically going through it and, looking at areas of chaos and resonances and where it, was maintained. And, here's just some mapping on some of the Earth moons that they call them, these ghost planets, on, the time frame here over billions of years, right? This is 4 billion year of simulation, and you can see how well constrained these different obliquities stay, even with these initial conditions. So when we're talking about a moonless Earth and the importance of a big moon stabilizer, most people just completely gloss over this or don't even know this particular ensemble study was done here in 2011. So this is a much more recent data on just this very question. And I don't think it's filtered out to the astrobiological communicators out there about maybe the big moon stabilizer is not the end-all be-all for astrobiology, questions about the Fermi paradox, things of that nature. The next article on our timeline is an EPSC abstract from 2013. And this is our large moon does not stabilize the Earth's axis. So now we're coming full circle here. 1993, it was absolutely essential. Otherwise, the tilt would be varying wildly between 0 and 90 degrees, 85 degrees. 2011, huge ensembles showing that without a moon, even the tilt is still well constrained. And now this abstract here is doing a quick rebuttal. It's not a big one, but just know that there's things out there. So this one is our large moon does not stabilize Earth's axis. And really what it goes into is the idea that our moon slows our rotation of our planet. And with a slower rotation, it allows for greater tilt variation. And if we could see right down here, we can see the normalized angular momentum and lunar mass and where we're going to have stable obliquity and unstable obliquity because of the planet it's orbiting slowing down. And 1,1 here on this chart is where our moon lives. And we are right near this line of instability for our moon being actually too big to have it be a stabilizing agent like it just claimed it is out there. So this is just another look that having a big moon stabilizer, if our moon was just slightly too big, the Earth may have been in a chaotic zone anyways, and the big moon would have hurt us. And maybe we would have been talking about why big moons destabilize planets, and how not having a big moon is so critical for life. If there was another planet in our solar system with like if Mars had a huge moon and we saw its tilt all crazy and wonky, we may have been arguing the opposite way on this whole big moon stabilizer thing if we had seen that in our own solar system. And then the final one in our timeline is 2014 on the spin axis dynamics of a moonless Earth by Lee and Badigian, where they look at a simplified analytic model versus the huge numerical approximations done in 2011, and work through it kind of analytically and find two chaotic zones and a bridge between them. And working through their analysis, they find that the Earth would diffuse through a chaotic region relatively quickly, and then maybe take a couple billion years to get through the stable bridge between the chaotic zones, which is, kind of said down here in the conclusion, where there is some rapid chaos regions, but that the estimates suggest that the time to cross the stable bridge is about 2 billion years, much longer than the time to cross those chaotic zones. And this is consistent with the findings of the Laskar paper. Well, this says 2012, but it was in 2011 about the numerical calculations. So although it's a simplified analytical model, they do say in here that endeavors of this sort really must wait for additional substantial breakthroughs and observational characteristics and analytical basis on it, but it should drive some analytical backing behind the numerical analysis done in 2011 about these broad regions of stability where it takes hundreds of millions and billions of years, if it's going to even move out of them, to move out of them. All right, so kind of where does that take us now? So the 1993 letter mapped where chaos could occur with present-day orbits, no tidal evolution, scanning some initial spin states. It's an envelope of possibilities, not a forecast. And later work refined that picture substantially. The large numerical calculations in 2011 showed huge areas where the tilt is constrained very well without a big moon stabilizer over hundreds of millions and billions of years. And then also the analytic theory that came after the numerical calculations backed those simulations, that the Earth's tilt would wander, but so slowly that you'd only cross tens of degrees over billions of years, and would not flip wildly from 0 to 85 degrees over the span of a few million, or even in the span of a few millennia. So the big moon stabilizer idea that is just out there needs to go away. Is the only way to say it. That modern looks at that modern ensemble calculations really show that the Earth's tilt is fairly stable, at least over very large stretches of time, where you wouldn't have these wild flips in climate, as the Earth isn't going to swing wildly about. In fact, the Earth is kind of on this boundary. Mercury and Venus, solar torque is completely dominated, and there is no tilt discrepancies. Mars is claimed to be the poster child of chaos, with its orbital tilt varying wildly between 0 and 60 degrees because it's so close to Jupiter. So even with the modern estimates, that's only 0 to 60 degrees, not 0 to 85 degrees like that was initially predicted with the Earth in the 90s. But even that still needs to be taken with a grain of salt, because we have zero physical evidence of Mars's tilt at all. That we just, we don't have geologists on Mars to look for signs of that. So everything we know about Mars's tilt in the past is also based strictly on just ensemble calculations. And I do find it a little convenient that Mars's tilt is 25 degrees and Earth's is 23 degrees, and it's just chalked up as coincidence, and that Mars truly is chaotic. But again, I'm going to take that with a grain of salt. As we can see in the span of 30 years or 20 years, our models may completely change what we know about tilt of the planets, and 20 years from now, we may be revisiting this completely again.